All right, everyone, let's go ahead and get things rolling here, and other people trickle in as this starts. So thank you all again for joining us here. This is going to be our final class for the moment here in our machine learning engineering series. So big thanks to everybody who's been with us. I know I've seen a lot of names in the classes here again and again here, so thanks for sticking with us. Hopefully this has been useful to you all. Today is going to be a bit different than the other classes we've had. If you made it to our last class, you might have saw we just had a really good Q&A session. So we just left the table open for any questions you all had in machine learning and data science here. And there were no shortage of great questions here. Hopefully my answers were useful to you. So if you haven't seen that one, I do encourage you, go back, check out the video here. This class is meant to act as a recap of sorts for everything we've done so far. So throughout this entire course here, we've really dug into building models with TensorFlow. We have turned around and learned the syntax of TensorFlow, how to use it, the tools it provides, TensorFlow data sets, and TensorFlow model serving and other things in that ecosystem. We've learned about some of the best practices for training and running a model, doing distributed computing, using GPUs, TPUs. We've learned about some of the tricks and tips that the best machine learning engineers and data scientists actually use to make sure that this all goes smoothly and efficiently, so we can, get to a well-fit model that does what we need to do as quickly as possible. And we also learned about some of the common pitfalls, tips and tricks, how to avoid overfitting, how to deal with it, how to check your model's performance on certain things here, how to do early stopping so you don't spend too much time and money training a model that's just overfitting. We threw a lot of stuff at you, and we did it over the course of a solid 2 months. So what we're focused on doing here, and one thing that I really like about Elephant Scale's style of teaching, is we try and make sure you focus on learning by doing. So a good measure of success for is this a useful class for our students is, can they do the things we've taught them to do, right? Because at the end of the day, you may be kind of a person that enjoys tuning in once a week to hear me drone on for 2 hours. But my guess is your goal is to be able to actually use this stuff. So today we're going to test, can we actually use this stuff? We've gone ahead and created an empty notebook here. This is going to be in the link, the bit.ly link that we have for each class here. Suji, would you mind dropping a link to this, to our folder here? And you know what? I think I can actually do the same thing here. Let me see. So we are in, I believe it is this folder. Yeah. So this is on the bit.ly link in the file that you've seen again and again through each one here. But I'm going to get a shareable link here for this folder, and you can access the one we're working with here today. I'm going to be live coding this. So this is going to be a bit different than other classes where the notebook's already been prepared and we're just kind of talking through it. I want you all to really get a feel for the order in which we deal with some of these things, because reading completed code and understanding it is not the same thing as being able to generate it. So the goal here is to give you all the ability to ask questions line by line as we write this out here. And we are going to build, train, tune a model. And we're going to follow all the best practices we've talked about so far. We're going to build an optimized data pipeline for it. We're going to use all the great TensorFlow callbacks we can use here. We're going to iterate on our model design. We're going to change some hyperparameters. And we're going to do it all on GPUs and TPUs here. And you'll see that the cells are empty, so you can live code along with us. I will drop this link in the chat window here for this Google Drive folder. You should be able to access that. This is the same link that the bit.ly in the Google Doc always goes towards here. So you can go ahead and use that. When you do see this document, please make a copy. Do not try and type code. I don't think I have the settings. let's see here. So it looks like, did everybody see that link okay here? Suji, it looks like I dropped it to all panelists here. Can everybody see that, the Google Drive link? If somebody could please give me a yes or no in the chat window here, that way we can make sure you've all got access. Not in chat. Oh, all panelists. Whoops. Sorry about that, guys. I see what I'm doing here. Thank you for that. All panelists and attendees. You think after 8 weeks of this, I'd at least understand how to work Zoom, huh? There it is. Awesome. Thank you all. Sorry for the confusion there, y'all. So if you go into that and you see, that'll bring you to, this link will bring you into here. This is what you should see when you click on that. We're going to be in 08, final class. Okay. And you can just double click on this and they're going to do open with Google Collaboratory. Okay. And then, so we'll do that. And once you've done that, you're going to want to make a copy. Okay. So you're going to want to save a copy in your own drive here. Okay. And that's going to be most useful to you all here. So I'm going to type on the main document here. Go ahead and make a copy now, or you can always wait and do this after here, and get a feel for it there too. Either's fine, but this way we won't all be typing on the same cell and messing things up. Okay. So I want this to be an interactive session. So please, 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 if you have questions about a specific line of code, or maybe you understand the line, but not why I'm doing this now and not later, or anything about the process, the methodology, the tools, things like that, today's the day. Go ahead and get those questions out here, okay? And you can drop them in chat, or better yet, if you could please use the question and answer functionality of Zoom, and that'll make it really easy for me to see these. I do have this up and running to make sure that I see all these questions. I can answer them as they come in. So without further ado, let's jump right into it, okay? So for today's challenge, we are going to be building a model to train on the CFAR10 data set. Now, this was one that we briefly encountered in, I think it was the second class when we did some stuff with GPU and TPU-backed computing here, but we didn't sweat the data set, the model, things like that. We were mainly focused on, hey, how do we make this fast? So today we're going to do this here, okay? So first thing I'm going to do is I'm going to adjust my runtime. Okay, and I'm going to start with a GPU runtime here. So I'm going to change runtime type. I'm already on GPU. You may not be. So go ahead and set that up. And then runtime shape, standard is fine. You do not need high RAM. This is not a big model here. We're going to build the convolutional neural network to do feature extraction on these images here and dimensionality reduction through pooling. We're going to go through and basically build a multi-class classification model to tell us if this is a horse, an airplane, a truck, a frog, whatever the 10 classes are for CFAR10. That means we need to start by getting our data set. So in the interest of simplicity here, we can just use TensorFlow data sets. You can always, this is something we covered fairly easily in an earlier class here. If you do want to load a data set yourself to turn it into a TensorFlow data set, it's just, tf.data.dataset. And there's you can use one of their methods like from tensor slices. That's boilerplate code. It's very simple, very easy to find. We have it in our examples here. You'll find it all over the TensorFlow documentation. So we can kind of skip that step here and just download it already split into training and testing for us here. Before I do that, let's get our import statements ready to go here. So I'm going to import TensorFlow as TF. We're going to import OS because we always need that. Let's get TensorFlow data sets and let's alias it to TFDS. And now the classics here. Import NumPy as NP, import matplotlib.pyplot as PLT, and then we'll set it to inline. And this should be good for now to get started. Now, if you recall, we can always use, if we want to see, hey, what are those stock data sets that TensorFlow data sets has? It'll tell us. We can use a method called list builders. And these are all the different things we can pass into a .load call, and it'll just grab that data set. And it always seems like there's more every time I look now. So we are looking for CFAR 10, and here it is. Right, so just good old CFAR 10, that's all we need. So I'm gonna go ahead and to clean this up here, I'm gonna comment that out and run it again so that shrinks on us a bit here. And now I'm gonna get my data set here. Now, if you looked at the previous code we've written here, and by the way, this is totally okay if you're writing this stuff, don't feel like you have to have the functions for TensorFlow data sets memorized or something like that. It'll come through muscle memory eventually, but do not feel like, oh crap, I don't remember these. I myself, when I'm writing these, I've taught this course, many times now. When I'm writing these, I still go back and just look at old code and pull it over. All right, good coders code, great coders reuse. So don't be afraid to do that here. So I know that I'm going to want my training and my testing data to come back separately. However, I'm going to wrap that in a tuple because I'm going to want some info. I want the metadata for this too here, and TensorFlow datasets is good enough to give me those. And all I have to do is call .load. I'm going to pass in CFAR 10. Okay. You'll remember there are some things that we need to tell it when we're using one of these pre-selected data sets here, like what's my split? And I'm going to say, well, give me it split into training and testing. Okay. We're going to have it structured for supervised. So first off, we're going to make sure this is where we get the info. Okay. And if I didn't have this, if I didn't have the with info equals true, then I could just remove this and pull this out of the tuple. Right, so this would be okay. I'll put this back here. I just want to show you this here. But if with info was false or just without it, right? So if I did this, it would return like that, right? It would return totally separate here. But since it's going to give, it knows enough to pop the splits apart here. But since I do want the info, I'm going to go ahead and put that back. Okay. I'm going to set with info equals to true. And then I'm also going to say as supervised. Okay. And again, that's important to remember here. We are looking to do supervised learning. So if we don't set as supervised to true, then our labels are just going to be another row in the data set. They're not special, right? So we would have our image and then the actual class here. So we do want those separated out here. If you don't have labels, you can't train a neural network. And certainly you don't want to leave your labels in there because that's how your model is just going to cheat. It's just going to read the answer key and fit to that. So if I run this, it should give me a download and it should work. Okay, and this will take maybe a minute to get things to work correctly here. And we're getting there. And again, I think it's wonderful to use these things here. You can go to like the CFAR website or the MNIST website, download these manually, set up a directory. That is a good exercise to do to get a feel for these things here. That's totally okay. But in this case here, don't sweat it. It's totally okay to use these things. And it'll feel like cheating if you're not used to data prep yet or data processing. Getting it pre-split into training and testing is awesome, and they make sure that they don't make mistakes that we might make. So use it when you can. Okay. So once we've got this, we get into the first real section where we really learn some interesting stuff, and that was how to build an optimized data pipeline, a data processing pipeline with TensorFlow. So at each section, I've written some challenge questions that we're going to discuss here. And if you're trying to measure how well do I actually understand this stuff that I'm learning here, one of the best things you can do for yourself is to test yourself on these things here. Because remember, like knowing how to do it isn't enough. If you can't communicate it, then especially as a data scientist or machine learning engineer, then that's going to be really challenging on the job, because people need to know how we're doing these things, and you need to be able to communicate and talk with other engineers or data scientists, or most importantly, non-technical stakeholders who don't understand any of this, right? So people who may not understand AI, machine learning, all the vocabulary we use here. So these are good things to challenge yourself with, especially if you're trying to move into this industry. You got to be able to talk the talk, not just walk the walk here. So let's start with this here. So first thing we're going to need to do is we're going to need to process our data. Now, we do this with any type of machine learning problem, right? We might normalize or scale our data. Since we've mainly been focusing on doing this with images, although again, images aren't special. You can do, you can do this with anything that is a two-dimensional shape here. You can use convolutions for feature extraction. So it's just great for basically doing feature generation and figuring out what they are. So you can do this here, but we need to process our data first. And we've seen we could go through and just divide every image by 255, but it's not really going to work for us, because essentially that's slow, and that would be done iteratively, and there's like 60,000 images here. So that isn't useful to us here. So what we can use here is a concept from functional programming. Again, functional programming can generally be reduced to the three major concepts: map, filter, and reduce, where I can give it a function, and I can say map, go ahead and do this to all these this function to all these different rows at the same time in parallel. And that's exactly what TensorFlow is going to do for us here. So we're going to start by building a data pipeline. But what we're going to do here, what we're going to do here is we're going to write a function that allows us to normalize the image. And then instead of using this on the data, the raw data itself, we're actually going to use the TensorFlow data set kind of object, its own functionality. It has map built in. We can hand it a function, and it will do a much better job of running this function on all our data than we could. It'll do it much faster here. So hi, Al. So the link is in the Google Drive folder that you'll see up there in chat a bit here. And yes, Fabio, today is the last session. That is correct here. We may do some more in the future, but for now, for this series, this is the last session. And again, all of our sessions are recorded. All the materials are out there too, so you can always go back and through them. And if there's anything we didn't cover, you're welcome to ask about it today. I know that there's probably a lot of areas you guys are interested in here, like how do I do time series forecasting? How do I do natural language processing? It's outside the scope of our course. If there is enough interest, we may run one later here, or we can point you in the direction towards some great resources to pick it up on your own in the meantime. I'll make sure we talk about that at the end here, okay? So we're going to start by writing a function here that we can pass in. Now, before when we did this, we just called this Normalize Images. Normalize Image. And it took in an image and a label. And remember, we have to pass in the label because we don't want them to get separated. When things get mapped around here, we want to make sure that that stays one-to-one, so that otherwise our data becomes useless, right, if the data isn't labeled correctly. Let's see here. We're going to continue. And we're going to do, so we need to cast it. We need to do two things here. We can do this all in one thing here. So what we need to do, let's make a list of things we need to do here. We need to normalize image by dividing each pixel value by 255. And then we also need to cast each image to float 32 data type. We don't know what type it is, right? It's probably float 64, but we don't need 64 bits to hold each of these pixels here. 32 is totally fine, is what TensorFlow expects. So it's good to shift that over here. And then we need to return labels along with, well, not new image, we'll say transformed image. Now I'm just writing my comments here to kind of give me a line here, but of all the things I need to do. But when we write it out, if you look back at the other stuff, you'll see we can actually do this as a one-liner. We can actually say, I'm going to return. So I can start by doing a tf.cast call, right? And I'm going to say I want to cast my image, and I want to cast it to, a float 32. All right, and once I have that, right, so it's going to cast this here, then I can immediately divide it by 255, right? And then I can actually say, I can return, because it's in a return statement, I can return multiple things from a function here. I'm going to tack on the label at the end there, okay? And if I do this, this is a great use case for this here. So now I can come down here and I can start building out my data pipeline, okay? And I can say train equals, and I'm just going to keep replacing it here. And this is, you can give them different variable names for each step. There's not really a reason to in this case, and it's generally frowned upon because that's going to use up a lot of extra memory. So in this case, it is totally okay to do this and kind of override. So the first thing we're going to do is we're going to do a map call. And we're going to use that function that we just wrote here. And we're going to pass in normalize image. Now, this would do it one at a time. You might remember that, we could do just this, and this is kind of, it's going to map it, but it's not going to give us the parallelize thing here, where it's going to be much faster. However, TensorFlow is smart enough to do this for us. So we can set a num parallel calls. We see this right up here in the documentation. And num parallel calls, we can say, hey, here's how many threads you should be using to do this in parallel. So I'm going to set that. Now, I don't know how many threads I should be using to do this in parallel. However, TensorFlow can detect it for me. And this is found in, I think it's tf.data.experimental.autotune. Okay. Now, again, if you're seeing this and you're going, this is overwhelming, how the hell am I ever going to remember that? It's totally okay. Again, this is the type of thing that is what we would consider almost boilerplate code. This is found in documentation all over the place. It's found in tutorials all over the place. Do not feel like you have to remember these super long, inside of this single parameter here. Don't worry about memorizing those. Just copy and paste them over from old code or from documentation, and eventually you'll get a feel for it and you'll be fine. Okay, so this is our most effective way to apply a transformation, right? But this becomes a good question here. So now, I've processed my image, but there's some other things I need to do in my data pipeline overall here. Feel free to drop it in the chat here. See if you can answer this. What are some other things that we might need to do in our training pipeline? And as a hint, are there any things that I should be doing in training that I don't do in testing, or maybe I do differently? Because if you recall, when we did this in a previous class here, we did identify a way that a methodology difference in our training pipeline versus our testing pipeline and why that is. And we will review this here. So if you're trying to quiz yourself here, see if you can answer this real quick. And feel free to type, if you want to drop it in chat, go for it. What are some of the different operations we'll need to do here, right? Right now we have this big old block of data and labels. It's been normalized and that's great, but I still need to do some extra work to get this in the way that it needs to be for a neural network to use it best, okay? So first thing I'm gonna do here is I'm gonna cache my data. And that's because essentially I've just done an operation that could be long running, right? This could take a lot of time. I take the old data and I'm gonna run some operation to clean it, to do something like this here. This can take a while. However, just like, it's like a video game. Once you've done the hard part, what's the first thing you do? You save your game, and we save it by caching, okay? And this will allow us to not have to pay that cost more than once, right? So if it takes, this is a problem I run into all the time in natural language processing. I need to run a bunch of regular expressions and strip out a bunch of numbers and symbols from text data and things like that. And it's very common for this step to take like 10 to 15 minutes, even when it's parallelized here. So I don't want to do that 10 to 15 minutes every time something needs to happen. So I immediately cache it in the memory here, and it's very fast to access it. Okay. So caching is one thing I need to do. Another thing I need to do here is I need to shuffle my data here. Now, it's already shuffled from, we saw, if we looked up here, it had a shuffling operation. However, it's always a good habit to do the shuffling yourself. There's no such thing as a deck of cards that's been shuffled too much, just too little, right? So for our training data set, we do want to build this in. Otherwise, it just protects us from, weird things where maybe the seed got set and it's always going to give me these same results, and I just happen to find a seed that helped a lot. My model isn't actually that good, like that sort of stuff. So first thing I'm going to do is I'm going to shuffle here, and I'm just going to call train.shuffle. Okay, and now I can get basically I need to tell it how many items do I have to shuffle. Now, this is why we grabbed the info. This info contains exactly that sort of information. So inside of here, I don't even know how many items there are in the data set. However, it's easy enough to get it from info. So I'm going to say info.splits, because again, I could have a different amount of in my training and testing set here. And I'm going to say train, right? Because I care about, this is the training pipeline. Testing will have a different pipeline down here. So I only want to get how many are there. And I'm going to check, I believe it's num examples. Yep, that works, okay? Next thing I'm going to do here, okay, neural networks, they work best in batches, right? We want our data in batches. You can do stochastic gradient descent to optimize your neural network, which is take one random example at a time without replacement until you get through the entire epoch of data. That can take a while, right? You can do just regular gradient descent where you do all 60,000 or however many at the same time and compute your update, and that takes forever and it's not very useful generally, right? And both of those are extreme. Where we want to be somewhere in the middle. We want to do batch or mini batch gradient descent, right? That's the optimizers we're going to use. So what we want to do is we want to break our data into chunks that are going to get fed into this neural network, and it's going to handle them in these chunks, and it's going to combine their weight updates. So this way we're not doing a bunch of shuffling, right? We're not doing too little, we're not doing too much here. So we're going to say train equals train.batch. We're going to set it to a batch size. We're going to do 128. Actually, I'll tell you what, let's go a bit lower here. Let's go to 64. Why not? Okay. Now, there is one thing left that we need to do here, and it is this one right here. This is a very leading question. So what is prefetching our data? This is a question you should be able to ask yourself and get some sort of semblance of an answer, right? So essentially, we're thinking about you have your data that is sitting in RAM. Your neural network is sitting in a different part of the RAM here, and you need to funnel your data over to your model. The model needs to do some processing. Both of these operations take time. But what we don't want to have happen is, if you have two workers, you want them working at the same time, right? Even though one of them, you want them blocked by each other as little as possible. So what we don't want to do here is wait and grab the data until after our model is done training on a given batch, because then our model's doing nothing while we're waiting for this data to be loaded in. So we're going to call a prefetch call. And what this is going to do is it's going to prefetch our data while the model is training. And what this prefetch does is while this model is chewing on all these numbers here and coming up with what the weight update should be, the neural network's actually learning, then what's going to happen here is, kind of on a background thread, the TensorFlow is going to grab the next batch of 64 rows and labels, So that way, as soon as the model's done, we've prefetched the data. It can just go right on to the next batch. So it's not going to stop and wait for the data pipeline to go and walk over here and get these 64 and walk back, and it's sitting there and idling its engine and burning GPU time, which is expensive. So we're going to say train.prefetch, and it's this is a best practice. You should always end your data pipelines with a prefetch call like this here. Okay, this is quite useful. So essentially, when we're doing this prefetch here, what we're trying to do is, again, we don't know how many workers there are here or how much it should be doing, because again, this is something that's going to do parallel processing under the hood, right? It's going to have multiple cores doing multiple things, and I want TensorFlow to just handle that. I don't understand that stuff deeply enough here, and there's no real reason. There would be no benefit to me doing it myself, even if I did. Okay, so this is a good training pipeline here. And if your code looks like my code, then you're in a good spot. Okay, we also have our testing pipeline, and this is going to have to look a bit different. So let's run it, make sure there's no errors. Woohoo, it worked. Okay, and it tells us the shape of our data. Now, it's important to remember, we're working with color images here. So whereas we were working with like MNIST and it was grayscale, there were black and white images here, that was just 28 by 28. These are color images. So each pixel has a red, green, and a blue value, right? So this is a 32 pixel by 32 pixel image, and each of those pixels is made up of 3 values, right? So this is going to be a two-dimensional convolutional neural network, but we're doing it across a tensor. Not just a matrix here, okay? So we're going to go ahead and set up our testing pipeline now, okay? And this is another thing you should be able to ask yourself. What are the differences between a good training pipeline and a testing pipeline? Okay, so, well, first thing we have to do is we did some image processing on our training set, right? So anything we do to our training set, we also have to do to our testing set. Otherwise, this isn't a good representative sample. The testing set is almost like it's like a control group. We're not trained on it. How do you do? Well, if your control group doesn't look like your experimental group in some ways here, right? In all the basic ways except for the one thing you're doing, then it's not useful to you here. So we need to start by doing this. We're going to say test equals test.map. And then we're going to pass in the normalize image function again here. We're going to do num parallel calls. We're going to set it to tf.data.experimental.autotune. Let's see here. Joseph, I see you have raised your hand. You have a question. If you wouldn't mind typing the question either in the chat window or the question and answer function here, I'd be happy to answer it. I just want to make sure we have written records of these here because we do like to go back and look at them and get a feel for it here. So as you type your question, I'm going to continue on here, Joseph, and I'm happy to answer it as it drops in here, okay? You might be wondering, what are the differences we need to do in terms of steps here, right? We talked about there was something. Joseph asks, how do we schedule the pipeline in real time? Are you talking about doing this on streaming data, Joseph? Is that what you mean? You can just drop your answer in the chat window if you like here. But essentially, if you're going to, if you want the pipeline to work on real-time data as it comes in, that's going to be on inference, right? Or you're talking about doing like a different sort of system here. How do you train a model on real-time data? That's a great question here. That is a harder challenge because you have to figure out essentially, so anytime you're working on streaming data, you have to kind of do things a bit differently, right? Because streaming data typically means you're working on a cluster. And on a cluster, it means you're doing distributed computing, things like that here. So you can do it. You can do machine learning on Spark, things like that here, using TensorFlow. The complexity is a bit higher here. I think it's a bit outside the scope of what we can talk about right now. I don't have a big streaming data set ready to go. However, it is possible. I can definitely point you guys towards some great tutorials. I know Databricks has some wonderful tutorials on this topic here. I know there's a ton of great stuff on YouTube about this. Oh, you're saying, no, how do we feed real data to deployed models? Want tools we use to schedule the pipeline. Ah, gotcha. So there's a couple things we can talk about here. If you're talking about doing this to a deployed model for inference or for training, those are two entirely different things here. So in this case, we might train a model on the CFAR 10 data set. And we might say, okay, this model has nothing left to learn. Okay, for inference, excellent. That's exactly what you mean here. So if you go back 2 classes here, we ended up, we did do something for all the ways you can do inference here. We got a full 2 hours talking about that. And we actually demonstrate how to throw up a pipeline. My recommendation is to use TensorFlow Model Server or SageMaker. And I'll actually make sure we cover that at the end of this class here. I don't know if I'll have time to actually launch the inference point here. But Joseph, the shortest answer is you're going to use, generally you're going to save your model in some way, typically as an H5 file or as a saved model file using like a checkpoint or from TensorFlow. You'll put it inside a Docker container and you'll use something like, you'll use something like TensorFlow Model Server here. And that'll help. Sonam, I see your error. So my guess is that it's saying list object has no attribute called map. So for whatever reason, your train variable is seen as a list, right? So you'll want to make sure that this is set correctly. So make sure if you have an error, it's probably in this line, okay? So feel free to take a look at that. This should return as a TensorFlow dataset object. A TensorFlow dataset object does have a method called map. A Python list does not. So that is why that error would be coming through here. Great questions, y'all. Thank you so much for asking them here. I'm glad glad we got some questions here. So I'm going to go ahead and clean this up a bit so I can see the new questions coming through. All right, and let's get back down to here. So before we, immediately did our processing, we cached, then shuffled, then batched, okay? With testing, we want this to be a bit different, okay? And the reason we want this to be a bit different is because we want every single epoch. Let's say we do 100 epochs of training. I want my model to not overfit to like the order of the training data. I don't want it to realize that, oh, you know, question number 2 is always 7, right? Like every epoch, it's that, right? And your models will figure out all kinds of ridiculous crap if you don't do this right. Essentially, what we want to do here is we want to make sure that our testing data is essentially frozen. We're going to make sure that in our training data, we want it random. We want it all over the place. They're going to see all the same number of examples, but the order is going to change every time. But we want to make sure for our testing, it's not that. We want to make sure it's the same order every time, and we want to freeze that out. So what we're going to do here then is instead of caching and then batching, we're going to batch and then cache. So we're going to, and that way when we get our cached testing data back, it's already in the same batches. It's going to be in the same order every time. So I'm going to say test equals test.batch, and I'm going to do this to 64. And then I'm going to say test equals test.cache, okay? And now, again, any good pipeline ends with a prefetch call. And again, I'm just going to pass in tf.data.experimental.autotune. And if we run that, that should work fine too. Great. Okay. Quick review on this section here. And again, training models is great here. Training models is the fun part here, but don't sleep on writing a good data pipeline here. Being able to do this is really important. It will save you some time. I see Fabio has a question. He says, we can make a graph to see at the moment the number of epochs is good, right? Yes, we are. We are going to do that actually down here. We're going to run TensorBoard, and we're going to have an awesome kind of visualized dashboard that we're going to run, and we're going to turn that on before we train the model so that we can see it run and change and kind of watch the performance instead of just reading a little, text output here. So good stuff all around. So we've got all that good to go now. So now we'll just need to do some imports, right? Let's import everything we need. So this is something you will start to get familiar with, which is kind of, okay, what are the things I need, okay? And you're always gonna need two things. You're gonna need your model object, which is a sequential object. So I'm gonna say from TensorFlow.keras.models import, and I want sequential. Oops. And there it is here, okay? And again, this is just like the skeleton. We're gonna add a bunch of good stuff to it here. The layers, the organs, right, that actually do the things. This is just like the skeleton of it here, okay? Now, that means, so we have the model, we have the layers. So let's get the layers. You say from TensorFlow.keras.layers, and I'm gonna import, conv2d, right? Because I wanna use a convolutional layer. Another good question to ask might be, okay, what other layers go with a conv2d layer? Now, generally, whenever we do convolutions, we're also going to do some sort of pooling operation, okay? Another thing to mention might be, you say, well, wait, do I need conv1d, 2d, 3d? And the way to think about this is, well, it depends on the shape of your data. If you're trying to do feature extraction on a sequence, right? So like stock data, maybe you're trying to do something like time series forecasting, or sometimes it's common to use conv layers to, if you convert sentences to sequences, right? And you kind of vectorize it that way. Sometimes you'll do that then. And that would be a one-dimensional convolution, right? We're working with an image, and it's easy to remember this because we say, well, how many pixels do I have? I have height and width, right? And that's 2 dimensions. I don't have a depth here. Sometimes you will. There are cameras out there now that are RGBD. They do have a depth element there. I think it's done through infrared or something like that. Not actually sure how they do that. I believe when you're working with a lot of medical images, like fMRI, that sort of stuff, those are often in 3 dimensions here, right? Maybe it's a 2-dimensional scan, but over time, being the 3rd dimension here. So then you would use a conv3D. So easy to skip over and not pay attention. Go, wait, why am I using 2D? They're not always 2D. If you're working with images for image classification, it's almost always going to be 2D. But this is something you should understand. It's not a magic number. It's just 2-dimensional, just like an image. Okay, so there's a couple other things we're going to need to use here as well. So recall back to when we did our first convolutional neural network, and I think class 2 here. We realized, well, the convolutional layers are great for feature extraction, right? They're kind of pulling these latent features out of our data, and it really excels with images, but not just for images here. But it doesn't do classification on its own. It's just learning the feature maps. It's just learning the filters. So in order to make classifications, we need a dense layer, okay? And then we realized, oh, wait, well, my data is going to be in a 2-dimensional format here, but it needs to be a 1-dimensional vector here. So how do I reshape it to go from the shape that this needs in a 2-dimensional image to the shape that this needs, where we just converted it all to one big long list? And for that, we'll use a flatten layer, okay? Umesh asks, what are the best practices needed to follow while creating test data for time series type of data? Umesh, that is a wonderful question, and that is a deep one. So that is a full 2-hour class on its own here. It's a bit harder to pull off. However, I'm happy to point you towards, there is a great course on Coursera from the TensorFlow team itself. They put out an entire specialization called the TensorFlow in Practice specialization. It's taught by an awesome teacher named Lawrence Moroney. And the entire fourth class, it's only about a 2-3 hour class here. It walks you through how to do time series analysis in TensorFlow. And they do spend a lot of time on that. So while unfortunately I don't have I don't have the ability to go through a time series data and show you how to do things like centered window versus trailing window, how to slice it up, how to do holdout validation with time steps. There is a best practice for that, and you can do it in TensorFlow, and it is fairly easy to do in TensorFlow. It's also it's also the last question on the TensorFlow certification exam, if anybody's thinking about that. You use it to, I think, predict sunspots. I would encourage you to look at that, and I'll certainly point you towards that link when the class is done here. I'll make sure I show you guys where to go from here. But great questions overall. So once we got this here, I'm also going to include, you might recognize these two here, batch norm and dropout. And this is just going to allow us, we may use it, we may not at the beginning here, but the chances are we're going to deal with overfitting at some point. This is a way to help speed up convergence and reduce overfitting. Okay, so we've got all these. We run the cell, it's working. Now we're getting there. We're almost there, y'all. So now we realize, okay, well, I could just go right into creating the model, but we should probably create our hyperparameters first. Fabio, excellent answer. Yeah, those are all the ones I would use too here. I'm not going to use any layer-wise regularization here. And I'm using the sequential API, not the functional API, so we don't need to worry about like input. However, that is totally valid if you've used that style with Keras before. For some of the more advanced models, you'll typically see people revert back to the functional API. So yeah, absolutely, good answer. So we're going to set our hyperparameters in a separate cell, okay? And while I'm setting these here, I want you all to think about this first question. What is the benefit of setting them here separately? And you'll see that I use all caps to denote this is a hyperparameter that's been set somewhere else. And the goal here is you should be able to explain why do this? Why take the time to do this? Why not just model.add and I'm going to set epochs when I change some stuff around, right? And I want to run it again, or I want to change how many layers are in this or neurons are in that. So we're not, you can go over the top of this and do it for every single layer. We're not going to do that. We're just going to do the ones that are not a default. So any defaults like filter size or something like that, if we wanted to use that, we would leave that alone. And that's fine too. But I assume we're going to want to iterate on some of these things. So we're going to separate these out here. Okay. So I'm going to set an activation function. And for this, we're going to use ReLU. Again, there's a ton of great activation functions out there, but ReLU is going to be one of your best. Okay. Rectified linear units are absolutely awesome. If you're doing a different type of problem, there may be a reason to use something other than ReLU, right? Maybe you're doing sentiment analysis. In that case, something like tanh or hyperbolic tangent function might be more useful to you. Sigmoid is there, although typically you try to avoid using sigmoid nowadays for anything but an output layer. So ReLU is your friend there. I'm going to set a filter size, and I want my convolutional filters we're going to learn to be of size 3-3, so a 3x3 matrix. I'm going to set a pool size, and this is how big the pooling operation we do, and our max pooling 2D layer should be here. All right, so this will be basically, it'll take a 2x2 grid and it'll replace that 2x2 grid with whatever one single value out of those 4 grid spots is the highest here. If we're doing max pooling, average pooling would replace with the average. And this is a way to maintain information but still reduce dimensionality. We're going to do input shape, right? And this is an important one, right? These are specific to convolutional layers. Epochs, we always have to tell a model, so we might as well tell it up top here. Activations, we're going to set at a bunch of different spots here, so we might as well set that, but you're always going to specify that. But input shape is something you'll always have to tell your first layer, right? What shape is my data coming in, okay? And we know it's going to be 32 by 32 by 3. However, since our data is going to be different sizes here, one thing we can do, since we, if we were using a different data set, our data set would be a different size. All images in this data set are the exact same size, right? But we need to be able to specify and say, hey, well, you can set this programmatically. So what I'm going to go ahead and do here is I'm going to use the info, that metadata that I got back here, and I can get the features. And I'm going to say, so of the image, I'm going to go ahead and say, of that image, give me the shape of that here, right? And this is going to basically return, if we resolve this here, we would see it returns a tuple that says 32 by 32 by 3, which is the shape of our image tensors, which is awesome, okay? We're going to set loss, and we're going to set our loss to sparse, categorical, cross entropy, okay? Now, you'll see this interchangeably. You'll see that it's either going to be categorical cross entropy or sparse categorical cross entropy. I have had people ask, what's the difference? When do I use sparse categorical cross entropy versus categorical cross entropy? And this is something that challenged me for a bit here. The answer, because you will get an error if you use the wrong one. It depends on the shape of your labels, right? So right now we have images that are labeled 0 through 9 for the 10 classes, right? You might have seen where we one-hot encoded our labels before, right? We've done this in previous exercises here where we said, okay, we did, I think it's keras.utils.toCategorical, and we pass that in and say, now reshape this to 10 classes. And a one-hot encoded class of, let's say it's class 2 out of 10, that would reshape to an array with 10 spots, and it's all zeros, but the second spot for, number 1, that would be, that's going to be where it is here. That would be flipped to a 1. Now, that's, if you had a one-hot encoded set of labels, you would use categorical cross entropy. We are not doing that. We are trying to get it to, we're going to leave it as an integer. I believe here is how it's returned with CFAR 10. So we're going to use sparse categorical cross entropy. This is something that really, from a functional standpoint, if you're interested in the math behind how these loss functions work, there are 2 different ways of doing the same thing. Essentially, the way they're calculating cross entropy. But you can just kind of pay attention and read up on that. Functionally, I find that if one doesn't work, use the other. I mean, you need to understand what shape your labels are here, but typically, if you're doing a multi-class classification problem, it's always going to be categorical cross entropy as your loss function, unless you have a reason to use a special one. For something like for facial recognition, you'd probably use something like triplet loss. For binary classification, you would use binary cross entropy. So this is definitely something where you do need to have a bit of trivia. You do need to be able to either remember or be able to look up effectively enough here what loss function you should use. That's going to be dependent upon the type of problem you're trying to solve. All right, 2 more hyperparameters to set. We're going to set our optimizer. Okay, and this is where we could use SGD for stochastic gradient descent. We could use RMS prop. We could use all kinds of fun ones here. We're going to use Atom, that trusty workhorse from OpenAI, for adaptive moment estimation. And we didn't go deeply into Atom or any of the optimizers here. We just kind of briefly talked about what gradient descent is and how optimization works. However, Atom is worth looking up here. So anything for adaptive learning rates. You may have heard us talk about in previous classes how learning rate is probably the #1 hyperparameter you need to tune. Well, the cool thing about Atom is it's an adaptive learning rate optimizer. So some of your neurons are probably going to need different learning rates than others. So what Atom does is it provides a way to calculate that and switch that up. So if you have, these neurons and they probably need a very high learning rate because they're very far away from where they need to be, right? Versus this one's getting there, it might start to slow down. Atom is awesome for that here. So that this is kind of a learning rate, an adaptive learning rate strategy here. So Atom is a good one to use, RMS prop, momentum, all these are the good ones here. These are ones where if you want to know that here, I would encourage you to dig into the theory. And this is where you start to get into some vector calculus. And it starts to get kind of gnarly here. However, don't let it scare you off, because at the end of the day, we can still write good code and just use them. So we final hyperparameter I've set is number of classes, so I can set my output here. Now I can build our model. So let me run this. Okay, and now I'm going to start by creating our model here, and I'm going to set this equal to a sequential object, and it's totally empty. We could pass in a list of layers just right here, and you'll see this. If you look at the Coursera course from the TensorFlow team, they tend to do it like this sometimes. That's totally fine too, right? Where like if I had a dense layer, I would set a bunch of hyperparameters in here, and I would say, oh, and I want my next layer to be a dropout layer. Now we're not going to do that. I like to set these up in a much cleaner way. I like to just do model.add, and the order we add them is just like appending to a list, right? You take the next open spot. So it's a convolutional neural network. So we're going to start with a con2D layer. Okay. And again, we're going to instantiate this con2D layer inside the model.add call, right? And I'm going to pass in, I need to set some things here. So like, for instance, how many filters do I want? I'm going to start by learning 64, right? And we've already set filter size. So I'm going to set that right there, right? And that's my kernel size, right? And then I'm going to go ahead and I'm going to set some other things here. So I'm going to say activation equals, and let's set activation. Now, again, I could also just do this, right? I could totally do that and it would work just the same here. However, again, for iteration purposes, it's much easier to make a switch up here because you might run multiple experiments in a notebook, right? So this way, once I build the model by setting my hyperparameters up here, I don't actually have to touch this part. I can leave it alone, which is important because then I'm less likely to throw off the shapes of things here. And I'm going to set input shape equals input shape. Okay. And we should be good there. Now, you may remember there were a couple ways to do this here, but typically you always run your convolutional layers in the same order. You always do conv, relu, max pool, conv, relu, max pool, right? So this way we learn a convolutional filter. We use a rectified linear unit activation function, our relu, to zero out any values less than 0. So basically only tell us if you think something, how much you think something looks like something. If it's greater than 0, don't tell me how much it negative looks like something. It's not useful. Right? This is kind of what the model's learning, if we understand it into a level here. Now, you will sometimes see people do model.add and you do conv max pool. That's fine too. You can do conv relu max pool. And again, the relu is inside of this. It's not model.add. It's not conv relu max pool in like 3 separate model.add statements. We set the activation function in here. Okay. I'm going to go ahead and do a max pool layer. And we can always come back in and add another conv layer in between these and see, does this improve our performance? This is not something we're going to know off the top of our head. There is no hard and fast rule to follow. So instead, there's going to be some experimentation and there's going to be following some intuition and tracking numbers. So that's why it's very important to set all this up early on, because we will be doing this here, right? So inside of this, I need to set a pool size, and I'm going to set pool size equal to that hyperparameter I set. I'm going to say model.add, and now I'm going to add a dropout layer, and I'm going to set, let's say, a 50% chance, and neuron gets turned off. Now remember, this layer right here is meant to help us deal with overfitting. So I'm actually going to cancel. I'm going to copy that out here, right? I'm going to comment it out, and we'll come back to that later. Okay. And the reason that I'm going to do this here is I want to see what the model looks like before I deal with overfitting. I want to know how much overfitting I'm dealing with. Then I can get a measure for how much did this help. If I don't know how bad it was without it, then I don't know how much with it actually helps, right? However, I will add some batch norm here just to see, just to help with convergence time here, because this again is just going to help it kind of normalize it so it doesn't drift and it learns faster here. So now that I have these, I'm going to go ahead and add another. I'm just going to copy, and I'm going to say, you know what? Let's do all this one more time here. Now, here I need to take out input shape because that's only relevant to our first layer, okay? Now, this is kind of, I think this is good enough here. I got 2 convolutional layers with max pooling. Now, again, you have to remember, you can't do max pooling too much because it's going to cut every single time it happens. It's going to cut the size of the image it's looking at in half. So right here, when I get it, the image is 32 by 32 by 3. After this, it's going to be 16 by 16 by 3, or depending on the type of padding here, it might be 15. It might drop to 15, right? It depends on if I use padding as valid or same, which is one we're not going to mess with right now. So this is going to drop it to 16 by 16 by 3. This one's going to drop it to 8 by 8 by 3. We might still have enough patterns that the model can figure it out at that size. We may not, and certainly doing one more, I hesitate to think that our model is going to be able to tell anything from 4 by 4 by 3 grid. So if we did a third max pooling layer, the data it's looking at is going to be a 4 by 4 grid of 3 pixel values. I can't look at a 4 pixel by 4 pixel image and tell you, is this a dog or a cat? You probably can't either. It's probably not realistic to expect a computer to do as well with that. So don't just tack on max pooling layers like crazy, right? This is sometimes why you see people sneak in a conv layer in between them, right? But I think for now, this is good enough. Now, this is our feature extraction section, right? So now I'm going to go ahead and flatten it here, okay? And this is essentially a reshaping layer here that's going to reshape it from 32 by 32, or at this point here, I think it's 16 by 16 by, or excuse me, 8 by 8 by 3 or something like that. Then what it's going to do here is it's going to reshape that by just concatenating all of those here. So it's just going to say, make it all one giant list of 3 pixel values here, right? So it goes from matrix to vector. Now, this is just adding a basic multi-layer perceptron at the end here, right? So now we just add a dense layer. And you can add 1 or 2 or 3 or more hidden layers, however many you want here, to do some actual analysis. I'm going to add 256 neurons. I'm just making that number up. And I'm going to set my activation to ReLU, or better yet, let's leave it at activation. Okay. And notice I do not need to set the input shape here. It's going to do that naturally because it's going to pass that along. It's going to say, well, the shape it came out to was this, and that's going to pass along to here. So we don't need to worry about it. Okay. I'm going to add an output layer, which is another dense layer. However, it's going to have, it needs to have 1 neuron for each potential output class. Okay. And again, my model has 10 classes. So this is why I put num classes here. It's just a good reminder. This is what my output layer should be here. I'm also going to set a different activation function. ReLU is great for internal stuff, but again, output layers have special activation functions. So I want to use softmax here because I'm doing a multi-class classification problem, right? I want it to give me a vector, a list of 10 numbers where essentially they all add up to 100%. If you sum the entire list, it's 100%. And each number, each element corresponds to how likely the model thinks it is that the image it's looking at is that class, right? So if it's class 0 is dog and class 1 is cat and class 2 is airplane, right? If I see a cat, I should see a high number at the first element in my softmax here, right? I should hope that's high, and then the other should be lower. right? And these are percentages. We can interpret them as probabilities here. So I'm going to set an activation equal to the string softmax, okay? And I should be good here. I'm going to run that. And now it's always a good idea to run a summary of your model and get a feel for how big is this model. And this is a way to kind of look at and say, well, you know, one, is this something that I think can train in feasible time? Can I make it bigger? Can I make it smaller? It's good to look at your output shape. So yeah, see how we went from 30 because of that first conv layer, it shaved off 2 because of the padding here. Then that 30 got cut in half to 15. We did another conv layer, which shaved 2 off, right? And then we cut that in half and it's down to 6, right? So this is by the end here, this is a 6 by 6 by 64. And you might be wondering, where's that 64 come from? And remember, that's how many filters we set here. And that's how many filters we set here. So if we change this one to 128, we would see this one change to 128 and it would kind of carry down, okay? So we can kind of steer that ourselves. So we've inspected this, everything looks good. So we've got our model created, we've got our hyperparameters set, we created a data processing pipeline that's good to go. So now we're almost ready to model it, right? But before we do, we're going to add some TensorFlow callbacks. So you might remember these callbacks as just the most helpful things I think we have in our TensorFlow toolbox here that allow us to add programmatic behavior to our models during training, right? So I want to do a couple things. I'm generally going to want to do some of these things every time. First thing I want to do is I want to always save my model when it reaches a new best level of performance. So I want to take a snapshot anytime it breaks a record, right? If the best I've seen is 80% validation accuracy, if that's the metric I'm tracking, right? If it's, it was 80% the best I have, and the next epoch trains and this one gets to 81% validation accuracy, then I want to overwrite the model checkpoint I have, and I want to save my model at this one, not that one. So we'll use a model checkpoint for that, right? I may want to do some other things. Certainly I want to use TensorBoard to track a model here, so I'm going to set that up too. And then finally, I might use something like early stopping, or maybe something to adjust the learning rate, where I might do something like reduce LR on plateau. So I'm going to go ahead and set those up, okay? First thing I need to do, since I'm using TensorBoard, is I need to have a file, or excuse me, a folder called logs. So I'm going to do make dir logs. Okay, and we'll know this works because if I click on the file system over here in Colab and I refresh it, I'll see right here's logs, right? Great, I got an empty folder called logs. That's exactly what I need, right? Now, every time you run the model, TensorBoard is going to fill this logs directory, because we're going to set it as the path, with the logs, right? So what you want to do is you want to either use different folders for logs for each model, right, which is easy enough to set up, right, with some extra code, or you want to go ahead and just delete it, right? Like it's very common to go, ah, crap, this didn't work, and delete it, and reinstantiate this here. So I'm just gonna, for the sake of time, we're gonna run it, and if it doesn't work here, I can always just RMRF the logs folder here. So that's good, that's set up. Now let's set up a file path, and that file path is going to go to where we're going to save our model. So I don't have a folder called saved model, although although when I pass this in, the checkpoint callback will create one for me. So this will create a folder in our current level. It'll be right here when we run it, called save model, and that'll have our save model checkpoint stuff in there here. So I'm going to set an early stopping callback, right? And I'm just going to get this from tf.keras.callbacks. And there's early stopping. I have to tell it some things here, and I'm going to say, go ahead and stop on, let's say, val loss, right? And I might tell it something like, what does the minimum delta need to be? And I might tell it the patience. So I'm going to set a patience value of let's set a patience value of 3. So if we go 3 epochs in a row where validation loss isn't going down, right? Well, you know, if we hit 3 in a row where it isn't heading down, then we know, okay, this model's probably started to overfit. It's done learning as much as it can learn, right? So we just created that callback. Let's create a tensor board callback. Tensor board CB, okay, and oops. And it's from tf.keras.callbacks.tensorboard. Yes, Fabio, we will be sending out an email that has the recording for the class here, so you'll be able to finish it up. Thanks for joining. So now I need to pass in, like, well, what is the log directory? All right, so I'm going to say, oops, log dir equals, and I need to tell it where is it doing this? And I'm going to go ahead and say, well, I created a folder for this, so I'm going to call it /logs, right? Because that's the path to this guy. Basically, whatever the path is, and again, you don't have to do this here. If you're storing your logs somewhere else, just put in the path to whatever that folder is, okay? And that's totally fine too, okay? And I'm going to tell it some things like write graph equals true, write images, because maybe I want to look at the shape of my model here is true. I'm going to set a histogram frequency to, let's say, every 5 epochs. It should update the histogram of weights and things like that. And then finally, I'm going to say, oh, I think that's it. And that should do. Now, again, this is another one of those things that I look up every time. You do not have to memorize these. I certainly don't. What's most useful with your summary writers and TensorFlow and TensorBoard and things like that. Just look at the docs when you need it. It's something that there's a lot of different ones there, and some of it's useful, some of it's not. But it's very easy to Google. It's very easy to look at docs. So don't waste your brain power. Now I'm going to create my model checkpoint one here, right? So I want to create model checkpoint. So I'm going to say checkpoint CB equals tf.keras.callbacks.model checkpoint. And this is where I'll pass in my file path. And I need to tell it essentially what to monitor. So how does it tell when it's hit a new best best score? Well, and that's according to what metric here. So I want to pay attention to loss. So I'm going to say monitor equals, I'm going to pass in val loss. Okay. Let's go ahead and create an early stopping, a reducing learning rate check one here. So I'm going to say reduce LR check callback equals tf.keras.callbacks.reduce LR on plateau. And same thing we did before. And again, don't feel like you have to memorize these, y'all. And I'm going to set it to pay attention to val loss. And I might need to tell it, well, how much should it reduce the learning rate? So I need to set a factor, set that of 0.1. And then again, how many, what is a plateau? How long should that be? So I'm going to say if the patience is, let's set a patience to 3, right? And this is going to shrink that learning rate when it starts to hit that plateau. It's not learning anymore. We find empirically that there is a reason to shrink the learning rate, and that could get helpful. So created my callbacks here, but I need to put them all into a list. And I'm just going to pass this list in when I train the model next, right? And I'm just going to say this is going to have my early stopping callback, my tensor board callback, my model checkpoint callback, and my reduced learning rate on plateau callback. And we're set on callbacks now, which is great, okay? We don't need this cell. Okay. Now, I included this cell in case we want to benchmark for tensor processing units instead of GPUs here. Remember, if you are doing, if you are using tensor processing units, if you're using TPUs, they're awesome. They're super fast for really big workloads. They're much faster than GPUs for really big workloads. Then you need to include this boilerplate code here. So you can just uncomment this and run it. I did not write this. This comes right from the TensorFlow team. Okay. And then you're just going to use the strategy.scope. Inside of that, you'll create your model and do that. So you do have to change things a bit here, right? We've already created our model and it's in a global scope, right? The only difference we would do here is you would say with strategy.scope : and then indented, you would recreate your model, and then that's the model you would compile. That's the model you would train. Okay. So I've left that here. For what we're doing, GPU is fine. We do not need TPU. In my mind, it's not worth the cost for this data set here, just because we're not doing a bunch of distributed stuff. GPU is fine. Also, you get way more GPU hours on Colab. So you're aware, for anybody that is looking to use TPUs and things like that, Google did just roll out a new version of TPUs. It's their TPU version 3.8. It's super fast. It is insanely fast. And if you want to use it, they give, I think, 33 hours a week on Kaggle. And it's the exact, Kaggle and Kaggle notebooks and Google Colab notebooks are pretty much exactly the same thing. They run on the same servers at the end of the day inside of Google data centers. So do not be afraid to take a look at that. If you want to use something that uses tensor processing units, but especially like the 3.0 versions, the TPU 3s are so fast. But you don't want to spend the money on Google Cloud. Check out Kaggle. You can make them private. You don't have to worry about a lot of stuff there. So it's a great place to benchmark and to get a feel for how you can do some of these things. So I'm going to leave this commented out here. I'm now going to load TensorBoard. Now this part's optional. We don't have to use TensorBoard when we train a model. And if we do, we don't have to run it before the model is trained. However, you can, and I think it's helpful to do that when we're watching things happen. So Jupyter Notebooks do come with a TensorBoard extension, but you have to load it. It's not natively loaded. If Jupyter Notebooks loaded every possible extension they could have, it would take forever and it'd be a huge waste of memory. So instead, we just load that here, and then I can just call it just like a bash command here, and I can just point it right towards the logs directory. Now, if I run this, it's going to spin up. It's going to start TensorBoard. And we're not going to see anything in here yet. And that's because our logs folder is empty, right? Probable causes. You haven't written any data to your event files. Well, look at that. Okay. Now, once we train our model, right, this is the point we're all waiting for. We're going to call model.fit. I'm going to pass in my training data set, right? I'm going to set my epochs to epochs. I'm going to set my validation data to the test pipeline I've created. And my callbacks are my callbacks. And now as I run this, oh, whoops. Well, I guess I got to compile the model, don't I? That's what I forgot to do. So great. We ran into at least one error here. I was hoping so. So I forgot to do this one. I forgot to say model.compile. And let me shift this up one level here. It's slowing down on me. There we are. One more down. So, and I need to set the loss here. So I'm going to say loss equals loss. Optimizer equals optimizer. And I need to set the metrics. And again, metrics always gets passed in as an array. And I'm just going to say, give me the accuracy. Let's see how it does here. Now I've compiled the model. Now I fit the model, and it should work. Success. And we're going to watch this kind of tick away for a little bit. We're going to try it for, a good 20 epochs. It may not train for 20. because again, the model might, early stopping might kick in, the model might plateau in terms of performance. And we see that the first epoch, where it's learning to split this data up and move it around here, you know, that one was a bit longer, it's about 16 seconds. Remaining epochs are coming in at between, you know, 7 and 2 or 3 or whatever. And that's because it's caching everything, moving it around here. So if we go up here and we see this is getting written as it goes here. So TensorBoard is going to basically check this logs directory about every 30 seconds. And every 30 seconds, it's going to update our line graph a bit here. So we can watch this change around. We can watch it kind of figure stuff out. And we can get a feel for when exactly we don't need to train anymore here. So it's going slowly but surely. And we will see some other cool things come out of this here. Like, let's see. Yes. So these are my weight histograms here. Right? So when we say, well, what is that? Right? Well, we're looking at, this is a histogram of the weight values. Right? So when you're paying attention to different neurons there, and you're basically saying, well, how many of the neurons have a value of, you know, what you want is them to be centered, right? So you say, well, right about here, and this is 0. Well, it looks like it's fairly normally distributed around that, aside from all this peakiness here. That's good. That's what we want. We don't want extreme values. It'll converge faster generally here. So this way you can pay attention to what it's doing. And we can pay attention to some of these other things here, what it's kind of putting out. There's all kinds of interesting information on there here. Let's see. Distributions for batch normalization, all that fun stuff here. This is, again, our graph here. This is the architecture of our model. I always love looking at something like this here because it's very easy to spit it out, download it as a PNG. You know, anytime you have to kind of talk about, hey, here's what we did, you're generally including this in a white paper or your Jupyter notebook or your PowerPoint presentation. So I think it's a wonderful visual to kind of show what does it look like, what do I got, that stuff's here. And again, we got all this good stuff here. So we're not using the images, but we do have this, and we can see, whoops, let's go back to that. And yeah, it's going. We see that kind of, I'll scroll the zoom. So if we zoom back out here, we can kind of see, whoops, where it is and what epoch we're at here. Right, and we see that this is kind of going up here. My training set is overfitting like crazy comparatively. So if we go down here, we'll see this here as well. And it looks like it got to about 5 epochs in before it quit on us here because our model had started overfitting, right? So it stopped early because we put on early stopping. And the reason we put on early stopping is because when we look at this, we can see that it kind of looks like that here, right? So this is not a good graph. We do not want that. That is a problem for us here, right? So sorry, I'm having trouble with my mouse trying to get this thing to zoom in correctly here. But yeah, this is all over the place in terms of my training loss ended up way down there. That's not good here because it left my validation loss behind, right? So let me zoom out. Oh, I see what it's doing here. We can do this. I can say, give me that. And it'll zoom in, perfect. And we can see, yeah, this is classic overfitting here, okay? So this brings us to what will we do here? Let's do this one more time, right? Well, I would probably come back up here and I would say, well, let's add in some dropout. So let's uncomment this and let's uncomment that, okay? And then we can do this a couple different ways, right? What I can do here is I can pay attention to this. I can just write down like what were my scores? How did it do when it ended, right? And I can see there's a couple metrics I care about. And those metrics are how long before it started to overfit. We can see after Epoch 1 almost immediately, right? And I care about how long did it take to train and what was the overall performance? What was the overall accuracy and loss, right? So essentially, I can just go down here and look at the numbers if you want to hard code them here. And I do, I write them down. I'll generally be like, oh, I got to 62%, right? I have notebooks full of, chicken scratch with that sort of stuff. Or you can kind of keep this out open here. Like for instance, if you're wanting to do comparisons here, I can always create like a logs 1, logs 2, logs 3 folder and point them at those here. So for the sake of simplicity, let's do that rather than, or actually I take that back. Let's delete this logs folder. And then we'll do the same thing again. We'll reinstantiate it. So I'm going to say RM, RF, and I'm going to say logs. And that should delete this folder. And again, if we refresh it, we'll see that's here. Tensor board is going to yell at us very quickly here because it's going to try and pull data and see it's not there anymore. I'm going to recreate this logs folder. Right. I'm going to recreate all my checkpoints. Let's set a higher patience value this time. Let's set an early stopping a patience of 5 instead here. And let's leave the patience for reducing our learning rate callback the same. We've gone ahead and changed some of that up here. Okay, we don't have to touch anything for this here. Model's compiled. We do want to recompile our model because we made changes to the architecture, right? We added some dropout layers. So we're going to train it one more time here. And we should see the dropout helping a lot. Although, let me double check because I'm not sure. I can't remember if I actually, I don't think I did. I need to rerun the cell where I added the dropout cells. Yep, whoops, my mistake. That looked too high. So this is an important error to pay attention to. You notice I changed some stuff. I didn't rerun this. I recompiled it, but again, I hadn't rerun that. So it didn't add things around here. And we saw my accuracy was super high for training, first epoch. And that's because the weights, I mean, the neural networks are stateful. The weights are stateful. So I hadn't deleted the previous model. So if you call fit again, it's going to start where the last model stopped. It's the same model. It knows as much as the same model previously did. So it's very important when you you're going to do it again, either do it with a different variable name, or you have to go back up here and overwrite it, right? So now this right here wipes out the model that was in the model variable namespace before, and it rebuilds it with all this good stuff, and then we compile it. So I'm just going to run down the list here and run this one more time, and this should work now, and we'll have a fresh start. All right, and it's getting there. And that looks more realistic now. It starts out at the low 30s and it starts climbing here. And what we're going to be interested to see is does it start to overfit as quickly here? Hopefully it doesn't overfit as quickly, which gives the model more time to train and learn generalizable things here, right? And we see, yeah, actually it's doing much better here. So we'll see as this starts to come in. The other one started to separate by Epoch 2. And its early stopping kicked in at Epoch 5. And we see that validation accuracy so far monotonically increasing. That means our model's learning. We can see validation accuracy and training accuracy are staying about the same time here, right? Although, we just saw this go back down. So maybe this is where it's starting to overfit. We will see. And it's certainly possible it's thrashing a bit here. So our model isn't quite converged yet, but it is still learning. It is still getting better. This is exactly what we're looking for here. Paul has a question. He says, my tensor board is showing error 403. What is the problem? Paul, I'm not really sure. It's a good question. Could be a number of things. I would make sure that your tensor board that, let's see, could be a couple things here. I would make sure you have tensor board extensions loaded directly. You've got the log directory set up correctly here, and that your tensor board callback here, make sure this is set correctly. Typically, I find that's one of the errors. It could also be a permissions error. Tensor board itself is a web server by Google. It spins it up and runs it locally on your machine. So if it is a permissions error, something like that, you can generally, tensor board's got really good documentation and a million answers on Stack Overflow. You can typically Google that question and say, here's my code, error 403, what the hell's wrong, tensor board? I'm sorry I don't have a more direct answer for you here, but that's how I would solve it if it was causing it for me here, because that's not something that's happening to me a ton here. And we see this one actually got through the full 20 epochs. Got to good validation accuracy. We're just starting to see a little bit overfitting, but that's generally where you want your training to stop, right? That's generally what you're looking for here. So I'm going to go ahead and back this out a bit. We're going to zoom in to this here, and I can just do, whoops, I can just do, give me that. Well, and let me say, I don't want it to go to there. That's scaled correctly, right? And now I can go here. I can do the same thing, and I can say, well, show me all of this loss. I can zoom these in, and this is much better model performance. Now, I would probably even try training for another 5-10 epochs here, because although the model has started, my training has started to pull ahead of my validation, it hasn't separated a ton yet, right? And that means that although the model may overfit in 3 more epochs, it may learn enough to get another 2 points of validation accuracy in those 3 epochs before overfitting kind of scorches the earth here, okay? So it is kind of an art and a science to figure out how to deal with overfitting, how to get the most performance out of your model. But this is great. This is exactly what we're looking for here, okay? Now, this brings us to, let's assume that we have finished this model here. We are in a good place, right? And we are ready to productionize it. So we don't have time to go into like shipping this completely and spinning up an endpoint. However, TensorFlow Model Server is your friend. And again, we did talk about how to use Model Server in a previous lab here. I believe it was 2 classes ago. So do take a look at that, 2 or 3. Take a look at that. That talks you through how to throw up an endpoint using many different approaches here, from Docker and TensorFlow Model Server to Flask to SageMaker, which I think is my personal favorite here. So for this here, what's important is your saved model folder, okay? So you see, if you look at what's inside saved model, you have assets, variables, and saved model.pb. If you have that, or you can save it as an H5 file using H5Py, which is a library that people love to store models in H5 format because it's smaller and easier. It's 1 file instead of 1 folder. Then essentially all you do is you're just going to load your saved model into that Docker container. You make sure you keep the right structure that TensorFlow Model Server requires. And if you just follow their instructions, it's dead simple to spin up an inference endpoint using TensorFlow Model Server here. So that is a very quick, easy way. Notice you can also take this saved model checkpoint or an H5 file. You can use a Flask server and load that on the back end too, right? So anytime I have this saved model folder, I can load up my model at its best performance. And then I can use that model. I just call model.predict to get my predictions here. And then you can serialize that and return it as needed for whatever your inference strategy is. And again, there's a ton of great ways to productionize these models. I'm a personal fan of loading these up using AWS Lambda and serverless. Load the model as a request comes in and then make a prediction, things like that. I think serverless really is the future. But there's a ton of ways to do this stuff that are already optimized for you in platforms like GCP, like Microsoft Azure, or AWS here. So I strongly encourage you, take a look at those, see how they can make your life easier, because in my opinion, they really do, okay? So we've got about 20 minutes left here. We've reviewed everything, all the major high points we've hit, from how to train a model in TensorFlow, how to build it, tune it, use TensorBoard, all that good stuff here. We have 20 minutes left. I want to make sure that you all leave this last class with all your questions answered. So please, 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 if you have any questions remaining about deep learning, where do I go for this? What can I learn about that sort of stuff here? Let me know. Go ahead and fire them off now, and we'll make sure we get them answered for you. And while those are trickling in here, I'm going to go ahead and share where you can go for, if you want to do a bit more training. I know somebody had asked about time series or something like that here. Oops. Let me load this up here. And again, we are big fans of any sort of, any way that you can improve yourself, we think is better than nothing here. We're always happy to chat. I think we do a great job with instructor-led courses, right? So if you and your org want to level up, right, you say, hey, we really know what we want to solve. It's this problem that'll generate business value for us. How can we get people to a point where we can solve it? Elephant Scale can come in and help you with that. That's where we're really strong here. If you're just interested in learning more about this process, maybe you don't have a particular goal in mind here, you're just trying to upskill, there's a lot to learn, well then, good news, that is the #1 way people learn deep learning nowadays. They are not getting this from PhDs. The average deep learning and machine learning engineer is getting it from self-driven courses or instructor-led courses like we're teaching here. So here's one out from the TensorFlow team. Their instructor, Lawrence Moroney, absolutely awesome, runs a really good course here. And you'll see they do have 4 courses here. And this is just going to teach you a lot of what you've already learned in our class here. You'll find in this one, you know, hey, here's the workflow, here's a pipeline, all that good stuff. We kind of distilled it down for you here. And then they might go a bit deeper to explain some of these things, like, for instance, hey, what are the quirks around natural language in TensorFlow? Let's say you want to use an embedding space. You guys have seen the high points of these here, and you know they might go a bit deeper into some topics. We might go a bit deeper into others here. These two are animals on their own here, right? So how you deal with natural language and how you deal with sequences, those require a different bit of processing, some different strategies or model types when you're dealing with things like recurrent neural networks or sequence models. So these are awesome here, but I highly encourage you to take a look at them. And I'll also say, if you're interested in getting your TensorFlow certification, our course will get you half the way there, and then but they will ask you questions on these as well, right? So they have you build 5 models, and it literally just kind of marches down the list here for these classes. So I do encourage you to take a look at these here. I believe you can audit them for free, and if you want the certificate, it costs money. I see a question here come through. He says, is Colab at Google a good place to load a model for utilizing it? I believe, if I understand your question correctly, and feel free to correct me if I don't, when you say utilizing it, my guess is you mean for using it for inference, right? So we typically talk about machine learning in 2 separate phases. There's training the model, where we're creating the model and teaching it to do something. And then there's the part where we actually go and use it, you know, and you use it in a product, right? So that's when it's done learning and it's on the job now, it's hired, right? So Colab is very much for training, right? You're going to use Colab as a place to train your models. There are limitations where you can essentially go through you can train for so many hours before it kicks you off. However, Colab for free gives you a certain number of GPU hours, certain number of TPU hours per month or per week. They refresh, which is great. And that's awesome because it saves you a ton of money. And it gives you a place to just start coding and spin them up here. I myself, I have a machine that I built at my house that has a real nice, powerful NVIDIA GPU, so I can train locally and all that. And sometimes I still use it, but now more and more I find myself using Colab notebooks or Kaggle kernels, which are, again, the same thing, different website, to use their TPUs and their GPUs, because their GPUs are more powerful than mine, and regular people don't have TPUs. So for training, it's great. It's not something you can really use for productionizing your models. Something like that, your best bet is to use something like GCP or AWS, right? So use a cloud platform and use their tooling. Or if you're looking to do it for free and you're looking to do it really simple, then I would say Heroku is going to be your best friend there. Somewhere like Heroku, where you can drop in a Flask server or a Docker container that you can then load up this model, and you can just use that model.predict function on the data as it comes in and is pre-processed and all that, and send it back. Both of those are great solutions for throwing up a RESTful endpoint that can be consumed for inference for this model. So great question there. Colab is an excellent choice for training. For inference, not so much. And then Umesh asks, is there any site where we can refer to current available standard algorithms? Yeah, there is. So there's a couple ways that you can do this here, I believe. Let me see if I can pull them up here. I know Keras has, I think TensorFlow has a model zoo. Let me pull this up here. TensorFlow model zoo. Yep. Here, I'm going to share my screen again here so you can see this. Okay, and let's see, is this it here? Yeah, TensorFlow models. Yeah, so they have a model zoo, which is essentially, here are the, Umesh, to your question here about what are the standard algorithms here, well, there's the standard pieces of algorithms like that you need to understand, like what is a convolutional layer? What is a dense or a fully connected layer? What does a multilayer perceptron do? What are these things used for, right? And then you have other things where you say, well, what are the best architectures out there that people use for things like image image classification, object detection, natural language processing, things like that. So those models that you would use for transfer learning, like MobileNet, right? So this is MobileNet v2 trained on the common objects and context data set with training augmentation, and here's the val set, right? So these are models like exception. There's VGG19 down here, MobileNet 3, all these other good ones here. This is a list that the TensorFlow team has put out, right? So it's the TensorFlow models section we're in here, and it's got all this good stuff, how you can load them, how you can use them here. So this is a good place to get a feel for these here. I would encourage you to pick a certain area that you're trying to learn, and then learn what the best in class models are for that. If you're trying to do something around object detection, you want to draw bounding boxes around all of the dogs and cats in this photo, then you'd probably be looking up something like the YOLO algorithm. YOLO v4 just came out and it's awesome, right? And if you're trying to do something like natural language processing, you're going to be using something like a transformer model. Totally different thing here. Totally different architectures, totally different areas of specialty. You can't learn them both. I did eventually, but I would start with one and kind of go from there here, okay? So great question there. I would take a look at those model zoos here. I would also make use of Coursera. There's a great website by an OpenAI researcher. I can't remember if Chris Ola has OpenAI or Google Brain here, but for instance, let me pull this up here. I think it's distill.pub. And this, yeah, this is the good stuff. So distill.pub is your friend here if you're trying to understand the theoretical part. Chris Olah is a famous machine learning researcher that has made just an insane, awesome, really cool blog that does things like Bayesian optimization, visualizing neural networks. There's a ton of things here. Understanding what a receptive field is in a CNN here. All these different things here, and they are excellent for, you can go into these here, and a lot of them are interactive, which is super cool. So you can kind of get a feel for what these things are doing and how it works. Yeah, it looks like that one was interactive. So as we slide this, you can see, and it kind of changes things. So highly, highly, highly recommend if you were trying to figure this out here. Oh, Paul, thanks for sharing. Okay, the issue Paul had was third-party cookies need to be enabled. That makes sense for TensorBoard. Cool. So distill.pub is a great one for the theory. It's not going to cover everything. It's not a textbook. It's meant to teach you this here. I would also point out that textbook, though. So Goodfellow Deep Learning book. So if you're looking for the best textbook out there for deep learning currently, it is by Ian Goodfellow, who's the guy that invented GANs, Yoshua Bengio, who just won the Turing Award, along with Jan LeCun and Jeffrey Hinton. So this guy's super famous. He's one of the three fathers of deep learning, and then Corville as well is a super famous name. So this entire textbook, and this is, again, very deep textbook. It is parts of it aren't friendly. Like linear algebra, you see this goes into scalars and vectors and the math here. It pulls no punches. This is very much meant to be master's level, PhD level textbook about these things here. It's free online, right? And it's just deeplearningbook.org. Now, this is one that you're probably not going to read, cover to cover in a night. This is one that you're going to spend some time studying. You can buy a print version of it if you like it. I have a print version floating around here somewhere. But you can actually read, and the whole thing's available for free online, and it's phenomenal. So if you're really trying to understand the theory, and you're looking for maybe more classic way to learn it, you like textbooks, you like practice problems, you like doing the math by hand or by NumPy, highly recommend this deeplearningbook.org. That's a great place to go. And that should kind of help you through that here. Umesh also asks, what are the criteria one has to evaluate for the selection of a correct model for the modeling? Excellent question. It's going to depend specifically on the problem you're trying to solve. Essentially, these are going to be subject specific, right? So there's the classic ones that we use for machine learning. Accuracy, although accuracy's, accuracy can lie to you sometimes. Area under receiver operating characteristic, right? So AROC, that's a good one, right? To say, well, how does my true positive rate change with false positives, things like that. And you can do those too. You can, if you're doing regression, you're not going to use cross entropy for classification. You're going to use something like mean absolute error. So if you're doing regression tasks or time series modeling, typically MAE is your most common, either MAE or MAPE, mean absolute percentage error. Those are the ones that you're typically, that's the metric you're trying to optimize. So it depends on the task you're looking for. You might see some specific ones in domain specific areas, like for instance, natural language. Perplexity is a big one here. So it depends on the task you're trying to do. So I would encourage you to zero in on a specific project you're looking to solve, and then slowly try and become an expert on that project, right? So if it's computer vision, if it's facial recognition, take a look and read some blogs. There's a ton of great posts on Medium towards data science, things like that. You can always shoot us an email. We're always happy to answer your questions here and chat if there's something you or your company are trying to figure out. For instance, if you're trying to do facial recognition, you'd get into it and you go, okay, actually I need to be using triplet loss. And then triplet loss does this, that. And these are going to be things that are similar to what you've learned. Right? Nothing you've learned here is going to be wildly different unless you're going to like reinforcement learning is its own whole different animal. But with what you're doing there, you'll start to figure out, okay, how's this different? It's mostly the same. How do I change my workflow? And then you can solve those problems. So great questions there. I'm curious if there's a specific type of problem you're looking to solve here, feel free to post it to Mesh, and I'll tell you if I know it off the top of my head, I'm happy to point in the right direction. And I see we got about 5 minutes left for our last class here. I'm happy to answer any more questions if they come through. If not, then that's all we got. Thank you all so much. Thanks, Paul. Have a good one. You're very welcome. Thank you all so much for joining. This has been a lot of fun. And yeah, absolutely. Suchi, is there a particular email we'd like to give out here? You can always contact us through the Elephant Scale website. Absolutely. And I'm happy to give out my own personal, if you'd like my personal email here to chat about deep learning here, why not? guidovanrossum@gmail.com, but spelled silly. Oh, and perfect. Yeah. And hello@elephantscale.com is going to be the best way to get in touch with us here. And I recommend using that one here. All right, and I think that's all of it all. So thank you all so much for joining. And please keep an eye on the Elephant Scale website. And hopefully we'll see you next time around we do something like this. If there's anything we can do to help you, let us know. And we're always happy to chat, okay? Have a great day, everybody.